All right. Good evening. How are you all?
It was good.
You were good? So I'll give the midterms back Wednesday. So they're all graded. Just there's this administrative things we have to do with the midterms. Everything about the class. So there's this accreditation process that we have to follow. Anyways, so who's ready for a research presentation? Can we do it next Monday? This coming Monday?
Our group's planning for Thursday.
I won't be here next Thursday.
This coming Thursday.
Oh, this Thursday.
What was the plan? Yeah.
That was the plan, or
Was
is
the
it
plan.
still the plan?
I'm hoping it's still the plan. I mean,
I'll be here this
our
Thursday.
leader's not here, so.
But what other teams?
Planning on Monday.
Huh? Mark?
Planning on Monday.
Planning or finalizing on Monday?
It will be ready on Monday.
Okay. PLP team Monday.
Maybe Thursday. Maybe this Thursday. We're gonna look at stuff tonight and see if we can do it this Thursday.
So what I'm hearing, I can expect a finalized plan this Wednesday.
Yes.
Because next week, it's only Monday's the only option, isn't it?
Yes, next week I'll be traveling from October 15th to 20th. October 15th is a Wednesday, but I will be able to broadcast that night, right? So if you get your Gmail account, we can do Google Hangout. But I can only have up to 8 active participants. I can have as many viewers as I want, but I can only have 8 active participants. So it's first come, first serve. Right? If you emailed me earlier, I can add you as participant. It'll be recorded too. So Monday though, I'll be flying back in that evening. So it'll be a pre-recorded.
We have a question we can just send it to you in the Google chat.
Yes. So the Google Hangout will be open with 16 of us of the group, right? You can just send me a message.
Even if we're not in there though, if we have you on our Gmail.
Yes, if you send Gmail message, I'll get it too. So like a radio show.
We won't be able to watch until you upload it.
No, it'll be live.
Oh, it's live.
So if you can give me your Gmail account, I can invite you.
It's live even though we're not in that top 8. That's what I'm wondering.
Yes. So you can have viewers and participants. I can only have up to 8 participants. Last time I only have Jason and Stacy.
It wouldn't let me in there the last time. I was
I
watching.
invited you.
I know, and I kept going, and anytime I would try to go, I was watching it, and they would say, click this to go active or live or whatever, and I'd click that, it would close it. So then I'd go back to it and go through it, and I just finally gave up, just watched it.
Oh, you did watch it.
Yeah, I was watching while you're doing it, I just couldn't get into it.
Interesting. Well, let's do a test run beforehand then. Next Monday or next
We have
Tuesday.
to give you our email addresses?
Sure.
What? You don't have that set up database?
No, I have yours, that's fine. I have you, Stacy, Jason, and Charles. I don't think anybody else. Did you send me? I don't think so.
Sent you one before for the wiki. at
What?
that time. I sent you one before when I was doing the wiki.
Sure, if I remember. All right.
I'll send you.
So what do you guys want to do today?
Can you walk us through how to install PLP CPU with
Can we told?
the flowchart? Yeah, the PLP tool with the
What, Trevor, did you
flowchart.
show you?
This guy.
And
Works,
then,
right?
I got it to work.
Yeah, ask him.
Okay, I was trying to show him the other day.
he's like, oh, install that thing, sort of, or something. I don't know.
On the lab computer or your personal computer?
On my personal computer.
Should be easier.
I had a problem with Windows 8.
I've got
Then you don't use me.
PLP tool, just I couldn't get the flowchart generator to work.
I'll be in the lab this Thursday too, so I can help you there. Well, we had midterm last time. What do you think of the midterm?
What did you say?
Long is one of the feedback I have. Very long.
Average was what again?
773.
Okay, then I don't think we're material.
You want to go through the midterm next time when I have it? Okay. In that case, we're back to our schedule. So today, okay. Today we're going to talk about variables. So what do you know about variables?
They're dynamic.
Dynamic? Could be.
They could be local or global.
Yeah, that's what we're talking about today. What do you think the distinction is? Think about in terms of C or Java.
The
Scope?
distinction, as in the scope, like if it's a global in scope, you can call it from other,
You can access it
you can access it from other libraries,
from other parts of the code, right?
classes.
Yes, Charles.
I don't think global can be actively rewritten.
Yeah, you can,
Yeah.
unless you say it's a read-only variable. But you've been doing assembly programming and PLP CPU assembly for almost 2 months now. So in that context, when I say variable, what do you think of? Pointer? Pointer to a what?
Register.
Address.
To an address, a register? What do you mean by that, Larry?
Just a block of spaces where you could put data in, and you've given it an address. You've given,
Space.
yeah, and so
So do you think a register could be a variable?
sure.
So what do you think a variable is? If register can be a variable, if a memory location can be a variable,
Yeah, it's just
so how do you define a variable? What are the characteristics of a variable?
Data that can be changed.
Storage space.
storage space.
So what are its characteristics?
Allocated memory.
Memory that's allocated for storing space. How do you identify it? How do you do it in C when you're trying to use a variable?
Give it a name.
Give it a name, right? You give it a symbol.
Type.
So and that's the next characteristic, a type, which in the context of low-level programming, what is a type? It's what?
Hex or binary.
Storage size, right? You can have char, which is typically 8 bits in C, but it's not defined really. You have int, which could be 32 bits. You can have short, which could be 16 bits. So I keep saying could because why?
It's going to depend on the CPU if it's 32-bit.
It depends on the not the CPU even. It depends on the what?
Compiler.
Compiler. Exactly. So the CPU, let's say 8-bit CPU, right? You could still have long, like 64-bit variables. Who handles that difference? The compiler, right? But when you write in assembly, you don't have that convenience. Right? You actually have to do everything manually. For example, at PLP CPU, how big is your word? 32 bits. What if the programmer says, hey, I want a char, and I don't want to use the whole word. This is the last problem in the exam, right? I have a char, but I want to pack it to the same word. Now it's a mess. Right? Now you have to unpack when you want to use it by shifting and masking, things like that. Unpack. Your memory, the PLP CPU can access 1 word of memory at a time with low word store. And 1 word in PLP CPU architecture is 4 bytes. Now, if you say I have data type that's only 1 byte long, logically, if you don't want to waste space, you can pack 4 variables inside 1 word of location, right? You agree? But if you do that in software, in the program, you actually have to unpack it when you want to use it. That's the last problem in the exam. And you have like ASCII string packed into 4 bytes per word. So if you want to use each byte, sorry, or in the exam you want to print each byte, what do? You have to do what? You do a load word, you get the whole word to a variable, to your register. How do you actually extract each byte you want to print out to your? Mask and shift it. Right, because in the UART, when you store it back to the transmit register, it has to be on the bottom byte. So if you were trying to transmit the byte on the, so in this Wednesday we'll talk about that. We'll go through that program and see how this works, right? But the idea is variables can be multiple, can be different sizes. And the PLP and the CPU word size, it matters when you try to program in low level, but it's not really a limiting factor. Right? You can have 128-bit integer with PLP CPU. You just have to do more coding to work with them. Does that make sense? Yes, no? Philip?
Clear as, well,
Clear?
yeah, it'll get to me.
Let me ask you a problem. Say you have an 8-bit CPU, and you want to implement a 16-bit integer. So with an 8-bit CPU, let's say the registers are all 8-bit, right? So if you want to add two 8-bit numbers together, what do you do? Let's say you have 4 registers. Load 1 to register 1, load the second number to register 2, and then hopefully it has an instruction that can add those 2 registers, correct?
And just output both of.
Output the result to some register, some other register. Right? That's 8-bit operation. But what if you want to add 2 16-bit numbers together on an 8-bit CPU?
You want to add 2 16-bit
Numbers together on an 8-bit CPU. Is it possible, first of all?
I'm still not sure about the first one you said.
You have 4 registers.
Yeah, let's say you have 4 registers. The first one, you just add 2 8-bit numbers together.
What if your 2 8-bit numbers overflow or are the max value?
So that's how you actually do 16-bit numbers. Usually CPUs have a carry out bit signal, right? So when you have a carry out, that means the result cannot be represented by 1 byte. If you want to do 16-bit addition, you just make sure that carry out goes to the next addition. So in the program, you do it multiple times. So later in the semester, we'll try to do 64-bit arithmetic of PLP CPU, and you'll see how this works. Right? So
like it's overflow that
no,
loops
carry
back,
out.
or what's carry out?
What's carry in arithmetic? Let's say 5 plus 9. Do you have a carry?
Mm-hmm.
Yeah, carry the 1.
Yeah, carry the 1 to the next digit. Same concept.
Okay, so now to clarify that, if I have 2 8-bit additions, and they carry out, over larger than that, and I don't do anything with that operation, that's an overflow though, right?
Yes, if it's
If I
unsigned.
don't- Yeah.
If it's
I don't handle it,
signed, you don't know. You have to do other check.
right?
right.
If you don't handle it, that's overflow.
That's overflow for unsigned addition. But if you're doing 16-bit addition, you can use that fact to get that carry to the next 8 bits of operation. But you have to do it in software.
So you have 1 register with a 1 in it and another register with the remainder of your answer?
Yeah, you chain it.
Okay.
You'll see it. Well, in PLP CPU, it's a little bit harder because you don't have a carry out signal. But I'll show you it later. Anyways, the original idea is, even if you have 8-bit CPUs, you can do bigger, word size operations. Yes?
But isn't that is that a lot more work for the 8-bit CPU to do
Yes.
operations?
Because you have to do it in software, in program. So it needs more instructions to do it. Whereas in 16-bit CPU, you do it in 1 instruction.
Does the same apply for 32-bit and 64-bit?
Yes. A 64-bit CPU can do 64-bit operations in less number of instructions. So when a 32-bit CPU tries to do 64-bit arithmetic, you have to do it in software.
Mm-hmm.
That's right.
Cool, right? So when we talk about performance, that's important. That's why they sell different CPU sizes, CPU features. Why do people still use 8-bit CPUs?
Faster to calculate 8-bit operations.
Why don't you just always use 32-bit CPUs for everything?
Cost.
Cost. 8-bit CPUs are simpler and usually cheaper.
I guess
We've gotten to the point where it doesn't matter. Like we're able to produce CPUs with such a small feature size in silicon. Like we have, like Microchip has a 32-bit CPU and a PDIP package, which I think is kind of ridiculous, but it's pretty cool. So variables, right? Now we go into more details on the nuance on how to use variables. In your lab assignment so far, do you think you ever use local variables?
Well, most of the time.
All of the time?
So when we instantiate a words, we call it a local variable.
Really? Can you access that variable from anywhere in your program?
Yeah.
I guess it's true that global.
Even if you have a function, you have that label outside with the dot word, which is accessible from anywhere.
We haven't learned how to insulate a function from our initial variables.
Yeah, so you share that data, which is okay with small programs. But as your program gets bigger, sometimes you need some modularity, right? Because if you keep using global variables, think of it in terms of Java or C. Let's say you have a function, right? And then you put all the variables outside. Those functions don't get executed all the time, right? When they're not executed, your global variables will still exist and take up space somewhere, right? That's why you want to use local variables. When you're done with the function, it's gone, right? So scope is just where the variable resides. Like in Java or C programming language, it's usually marked with the curly braces, just to denote what the scope is. So a global variable exists throughout program execution, and it's accessible from anywhere. So if you have global variable A, which is only used by function 1, when the function 1 exits and never gets called again, A is still around. Right, so it's the disadvantage. Local variable exists only in a specific scope. So when that scope is over, that memory location gets free. So like variables within a function. The problem is when you write in C or Java, this is abstracted from it. You just know, okay, if I have int A inside this function, when this function exits, that memory location magically free. Have you ever wondered what's going on there? What happens there?
Windows takes care of it, garbage collection.
It's not even about garbage collection. It's just the structure of it. What data structure do you think they're using for this kind of bookkeeping? The wonderful what? When you think about something that needs to be saved temporarily, stack, right? So stack is a really wonderful data architecture. Let's look at bad code, right? So here we have 3 functions. So let's say this is being placed in that memory location in memory. So when we execute, when the CPU boots up, it jumps to func, not main. That's wrong. Jump to function. So here we have a global variable A, and we use it everywhere in this function, in this program. First we read from an I/O, and we pass it the address of A. So when you get the number from the I/O, the value from the I/O, it writes to the location A. And then you call the algorithm, which uses A. And then you print it out with that UART-write function, and magically you have A there too. If this is your program, like this is it, it's probably okay, right? You just call function once, you call algorithm once, you call print once. So who cares? Do you agree? Nothing wrong with this, right? But it's hard to read. Can you imagine going through thousands of lines of code and you see this variable, abracadabra? Where did this come from? Like you see the scope of the function, it's not there, right? And you scroll, oh, it's global, right? So things like this make code really hard to read, especially on long code. You want to make sure that your code is modular. And then if that function gets, like I said before, exits, that variable still sticks around, right?
It's okay to still have global variables.
It's okay.
Right?
Yeah.
Could be needed, so if something changes, you don't have to go back in and edit all of those.
Yes, if you want to have like a shared
currency exchange rate, and you've got a whole bunch of financial code that it's all these functions are dictated by.
that depends on what your program is to do, right? If it's like a low-level system program and you need to share a flag or something, that's fine, right? And then the other point is, what if function is recursive? What is a recursive function? Calls itself. If it uses a global variable and it calls itself, what will it do to the previous value in the global variable?
Change it.
It'll change it. Right? Maybe you still need that value when you return from previous level. Now it's gone. Right? So it would be nice if each copy of the function holds a copy of the variable. Right? So you make sure it doesn't clobber the previous level. So let's see this in assembly. So in PLP CPU, if you want to have like a space A, you can just do label A and then dot word 0. That initializes that variable to 0 when you start up the program. And then here you have, if you've taken C, this is passed by reference. So you're passing the address of A, not the value of A. And then and you expect this function to write it to the memory location. As opposed to here, when you pass by value, right? You dereference the pointer, get the value with the load word, and then we call the function. It's a little thing that if you've taken C, you would understand this. In Java, it's kind of like passing by object reference or passing by value. Remember that? Long time ago? Who's taken C? So you know pointers.
It was literally my first class at TCC.
So what is a pointer?
What's the address?
It's a variable that holds an address, right? Which points at that location in memory. So that's denoted by the star when you declare it. If you pass a pointer with the ampersand symbol, you're passing the address of the variable, right? If you look at the assembly, the load immediate will load the address to A0 and pass it through immediately. So the function needs to know, hey, I'm not passing a value, I'm passing the address where you need to write to. That make sense? On the second one, like on the bottom here, you're passing by value. So in the C, you do the star operation, which is a dereference. So when this compiler sees this, oh, I need to get the address, and then go to that address, fetch the value, and then pass the value. So this statement, if you look at the assembly, you will stick in a load word there. That's the dereference. You actually go in there and fetch the value. So all this time in the labs, it's kind of implied, and you do a load word, but this is actually what happens. So if you have a huge code, this is bad, right? Because you have variable A somewhere, and you don't pass value, you just assume that the functions will use it, which can be a pain, because what if the functions get called multiple times from multiple places? It could be really hard to trace and track. Any questions so far? So how do you make it better? Give me a few ideas.
Drop the A inside the curly brace.
Yeah, and then do the functions like the same person, and actually make sure you use arguments and return values, right? So but to be able to do this, you need to have local variables, right? So variable A will stay only as long as function is alive. The function is alive. When the function exits, that variable should be deallocated, should be gone. Right? So now all the three functions are modular, so you can call it from anywhere. Does everybody see that? Before, you have to use the global variable A, but now you just pass it a value and it should work from anywhere, right? And if function is recursive, then each call of that function will have a copy of A. So you won't clobber the previous A. Now the problem is, what if you have to write a compiler and the taskmaster, I guess, asks you to command you to write a compiler that can support local variables. So Jennifer said stack. Is there anything else you can use? How about that little storage spaces we have on the CPU?
Okay.
No.
Register?
Registers. Can we do local variables for registers? This is a deep level. This is like a new level question.
That's very good.
What would be the drawback?
Uses more, takes up register space.
And what if you do a recursive function?
You lose it.
You lose it. In the end, you have to use the stack, right? You agree? Yeah, because register is basically an architectural global variable, right? It's a real estate, right? So a prime real estate. Can you use register for global variables? Yes. But is that a bad idea? No? Yes, why?
Lose information.
Well, yes, because with using register, how many registers do you have? Few. In some CPUs, you only have 4. Right? So if you allocate one register to be a global variable, then you're just left with 3. Right? So registers are prime real estate. You want to make sure that you have register available when you do computation. Let's say you have like this little algorithm. Like if you can have the temporary values in a register, it'll be much faster. Let's say it loops 1 million times. Right? If you have to access memory a few times every time you loop, the algorithm will be much smaller. Right? So much slower. So you want to make sure you have enough registers when you do that computation. So let me give you an example. So let's say we want to do this operation, this expression. You want to multiply 3 numbers which are made up of those 3 additions. So if you have 3 registers available, here's what we can do. Load A to the first register, load the second value, add them and save it to the third register. Right, now you can add the next one, add that together, now you have Y. Now we have X times Y. Did you see that? So the first addition you get X, the second addition you get Y, and we can multiply those 2. Stacy is checking if my arithmetic is correct.
Oh, I'm just.
Okay. So now we only have to multiply with Z. So we can reuse 0 and 1 because they are done with, and then add them together, and now you have your final answer. Now, what if you only have 2 registers? What do you think will happen? As you can see, the font is smaller, which means more instructions. We get X. Now, what's the problem? We only have 1 free register left. So what do we do? Push it to memory, right? And then we can bring in the next ones, add them, push it to memory, and we can do the multiplication. So this is just to illustrate that registers are really prime real estate when you do computation, because typically accessing memory is slower. So if you use a 1 gigahertz, 2 gigahertz CPU, accessing the memory can be 10 times slower than just using registers. If you use tiny microcontrollers, it might not, it's not that big of a deal. But if you use a fast CPU, the CPU is much quicker than what the memory is. So that's something to keep in mind. So when you go to computer architecture, you'll see like why this is.
We're talking femtoseconds, right?
Nanoseconds. Femto will be, we're not there yet.
Yoda second.
Yoda a second? Just thought about Star Wars. So registers, right? That's why we may need local variables and functions. So let's look at our old friend, right? So how do you think you can implement a local variable with stack? Let's say you're in your function. Boom. The stack pointer is pointing at the right location now. What do you do next? You make space, right? You allocate some space. So how do you think you can do that with a stack pointer? How do you move that up?
Shifting? No.
Subtract. Right? If you just want one word in your, if you just have one local variable with one word, you just decrement by 4, right? You move the stack pointer up. Now you have a local variable in your function. So how do you actually use the local variable? How do you actually access it? Let's say, what? +4, correct. Right? So you just, let's say I want to write that value to the local variable. So all you do, you just store word, the value you want to write, the stack pointer +4. And that all sets into your local variable. Does that make sense? Now, before you return, what do you need to do?
You have to move your stack pointer.
Yes. Otherwise, what would happen?
Stack
Memory leak, right? If you don't deallocate, every time this function gets called, you add another word to your stack. And it'll never be cleared. So make sure you clean up after your mess and deallocate. You can do this just by adding 4 to your stack pointer. Is this clear?
No. Okay, the first operation, you shifted the stack pointer, the address of the stack pointer up one into F8, correct?
Yes.
Okay, now go to the second one. The second one, you loaded up the EF, and then you stored it into you shifted it by 4. How come
No,
you shifted
offset by 4.
Okay, if you that's what I meant. You offset it by 4. How come it didn't offset it 4 to F4?
It's positive.
Oh wait, those are counting. No.
Yeah, this is the end of the memory.
Oh,
never mind. Right, so you decrement the stack pointer to go up.
Yeah.
If you want to go back down, you
I thought that was the beginning of the memory.
So what if you want to allocate multiple words? What do you do? Multiple variables. So you, you decrement by multiples of your word size, right? So if you want 3 local variables, then you just decrement your stack pointer by 12 in PLPCP. Right, so now you have 96 bytes, 96 bit, so it's like 12 bytes of local variable space. And if you want to access each one, you just do the offsets like you saw before. Does that make sense?
Why wouldn't you just load it and then push it onto the stack? Why do you have to move the stack pointer? And like, why do you have to allocate how much space you're going to use beforehand? And then...
This way, you can allocate 3 spaces with one instruction.
Oh, okay.
If you want to do push, you do, right? And then you can access, with the offset, you can access it like randomly. Well, you don't have to go with the stack order.
Oh, okay.
If you want to access this one, you just do +12 and you get it with what words for. But I did the allocate with the add instruction, just make sure just to optimize and you just allocate in one instruction. Everybody get that? Everyone? So her question was, why don't you just use pushes to allocate? That way you can actually write to it immediately, right? So the reason you do it this way is because I can allocate 3 words just with one instruction. Because sometimes you don't want to write anything to it yet, right? So how do I deallocate these variables when I'm done with it?
At 12.
Add 12. Right, so make sure you destroy the space. So when you actually add 12, is the value still there? Yes, but conceptually they are gone, right? Because whatever is on here upwards, if you use your stack correctly, they are you should not access those memory locations anymore. Like you don't do stack pointer -4 and peek into the abyss, right? So it's dangerous. So make sure you use your stack correctly. This is how many vulnerabilities in programs happen. Because there's that one word that never gets popped. And then somebody got hold of it. Like, hey, in this program, if you keep calling this function, eventually it'll overflow the stack. And then you can insert your own code and boom, your program just got compromised. Right? So make sure you watch out for stack overflows. Any questions so far? Now, let's see how this thing is in action when you have a recursive function. Right, let's say you have that function that needs 2 local variables, 4 byte each, and it needs to call itself, for example. So you allocate 2, right? You do some operation, and before you call it again, you have to save the return address, right? So you save the return address. Now you're ready to call itself or other functions. When you do that,
Do you have to do the push RA, or doesn't the JAWL tell it to go to the RA?
can anybody answer that?
Oh, but that's the RA register, not the.
There's only one RA register.
Yeah.
Every time you call it, it gets overridden.
Yeah, never mind.
So before you actually go to the second level, you have to save the previous one, right? So now this is what a scope is in low level. So now if you hear the term stack trace or call trace or call stack, this is what they meant. So the stack is used to store all your local variables in your function and where to return. For example, when you write a Java program, it crashed, or you C program, and it crashed. When you want to see where it is, it unrolls the stack, right? So it looks at the stack from the bottom. Okay, you were in this location, you call this. You were in this location, you call this, and here where the error is. That's how you do a stack trace. Make sense? So this is where things are, right? So when you do a function call, you create a new scope. So you see, as long as the function is well behaving, your data there is safe from the previous scope.
If it gives you back and you do your stack trace and it says like stack trace and the error is 62, or stack trace tells you where it's at and then parentheses 62, what does that 62 indicate?
Usually it's the line number of the source code. So when you compile your program, you can include some debug information. For example, this function resides in this file, this line number. That information is extra space, but it's nice because when you crash your program, divide by 0 or whatever, something crazy, and then you can see, oh, it's from this source code line number 64, and you go in there and fix it, and then that's it. It makes it easier to debug. So the operating system, when a program crashes, it has this information. Just dumps the stack out, and then this is where you mess up. Cool? So et cetera, et cetera. If you call again, then you will have a new scope and so on and so forth. After you're done, if this is a well-behaving function, and you destroy those variables and you're back to your old scope, your previous scope. After you're done with that, you restore your return address, and then make sure you clean up your mess. So if you write a compiler, this is what you need to do, right, when you write a function or everything. If you code in C in Java, this is all taken care of for you. Right? This is one of the things that the compiler takes care of. If you write in assembly, no, you have to do this manually. Does that make sense? So you see the connection between high-level language, all the different concepts, the data structures, using array algorithms, and how memory is used and utilized, how you structure and organize your data in memory. And this is how the CPU can support that. Right, so this is the hardware-software interface. So you're delving deep into the core of the CPU and how it works. So this is the gateway to even more nerdness in the field, right? Like, because the next step, if you go deeper, you'll learn about actually building the CPU, designing the CPU, and how to actually execute programs. Any questions so far? Variables? Still processing?
Stack Overflow.
We can do some neat examples of the Stack Overflow later in the semester. How to break programs. You know how that's how like I'll talk about it after end the broadcast. If there's no question, then I'll meet you Wednesday. I'll have the exam, and we can go through the exam if you want. And the next topic, so this is the recap, all right, so will be the clock and the timer. So just for a preview, all this time when you program, there's no notion of time yet. Right? Conceptually, this is abstract concept, so this instruction gets executed one at a time, but there's no notion of time or how the execution relates with how we perceive time. Right, so that's next time. All right, if there's no question, then I'll see you Wednesday.